let's start with ionic bonding. Okay. Let's start with dot structures. We can use dots to show valence electrons. They're just called Lewis electron dot structures. And these Lewis structures of just individual atoms are very simple. We just draw a dot for each valence electron. Okay? And here we have elements going right across that second row of the periodic table. Lithium through neon. Okay? So lithium, if we just start with lithium, that's just one valence electron. Right? That's essentially 2s1. Okay. I'm not going to be too particular about where we put those electrons. Okay. This is really just a shortcut for orbital diagrams. Okay. Because really that would be one electron in 2s, and that would be two electrons in 2s. So I do kind of think it's nice sometimes to put those together. Okay? So now we got 2s2, 2p1. 1, 2, 3, 4, 5. 3, 4, 5, 6. 4, 5, 6, 7. And then finally 8, 6, 7, 8. All right. Remember, something like oxygen would be 2s2, 2p4, right? It would be something like that. If we put those p's all together, it'd be something like 1, 2, 3, 4. So that's sort of why I drew another two electrons that were paired, and then other ones that are unpaired. That's kind of non-scientific, but it sort of works. Okay. What's important, though, is we got to neon over here with its 8 valence electrons. Okay? And remembering that neon is a noble gas, that's going to help us out quite a bit. Those 8 valence electrons refer to which subshells being filled. What letters are filled when we have 8 valence electrons for just a noble gas? P and? Yeah. Those 8. So P just holds 6 electrons. Yeah. So we got a full S and P. Okay. All right. So that's just for neutral atoms. Okay? If we just had an individual atom somehow, we could indicate its valence electrons that way. An ionic bond, okay, just like we talked about, attraction of two oppositely charged ions. Recall Coulomb's law: if we have opposite charges, the energy will decrease as they get closer together. Okay? That's favorable. Okay? So what's going to happen, we can make a very simplified view of an ionic bond forming if we start with two neutral atoms. Okay. If we start with a sodium, right, that's under lithium, so that has one valence electron. And here, I'm just going to make the 7 on chlorine. I'm going to put the unpaired one over on this side just because it's a little bit closer. Okay. Now, what do metals tend to do when they form an ion? If we have something like sodium and it forms an ion, what would that sodium? A metal like sodium has one valence electron, so let's think of it that way. So what's going to happen? Is it going to share it? Not quite. It's going to what? Yeah, it's going to get rid of it. Okay? We're going to talk about sharing in just a second, but we have to think about what's the driving force for this. Okay? Because sodium has all full shells, and then it's got a single electron kind of hanging out there all by itself in that next shell. Okay? Ends up being 3s1, right? So if it got rid of that one electron, it can totally do that. Okay? that tends to happen because what we're left with then is totally full S and P, like a noble gas would have. Okay, so here we've got chlorine with 7 valence electrons. What should it do in order to form an ion? Yeah, and notice those are kind of complementary processes, right? This 1 electron here, lost from sodium, can be gained by the chlorine. Okay? We end up with Na, which forms what charge then after it's lost an electron? Yep, it forms a single plus charge. We've got chlorine, started with 7 of its own valence electrons, and now has 1 more new valence electron that it just got. That extra valence electron gives it a negative charge. Okay? So what we've made right here is an ion pair. Okay? It's just 2 ions that have opposite charges. Okay? An ion with some kind of positive charge, an ion with some kind of negative charge. They don't have to be equal and opposite, but one has to be plus something, one has to be minus something. That's just an ion pair. Okay? And then the attraction that those ions will feel is the ionic bond. Right? So it's kind of a 2-step process. If we started with individual metal and non-metal atoms, what's going to happen is a transfer. Right? This is an electron transfer, correct? We could talk about that as a oxidation and reduction because that sodium loses an electron, which means that sodium got what? Lose electron oxidized. Remember Leo, right? So sodium lost an electron. That chlorine gained an electron, so it was reduced. Yep. We got Leo over here. We got Ger right there. So it's essentially an oxidation reduction that happens anytime there's an electron transfer. Okay? But if we write out some electron configurations, we can see that pretty clearly. Okay, sodium, 1s2, 2s2, 2p6, 3s1, right? How does this electron configuration change when it is Na+? Yep, we lose that one right there. It's just 1s2, 2s2, 2p6. We have full S and P. We have 8 valence electrons now. Okay. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Here are our 7 valence electrons. So then what will be the only change for Cl becoming Cl minus? Yep, 1s2, 2s2, 2p6, 3s2, 3p6. Okay, see them right here. Now we have, again, full S and P, and again we have 8 valence electrons. So look at our octet rule. Main group atoms, that's atoms in the S or P block generally, they tend to become stable when they have 8 valence electrons. That has everything to do with electron configuration, okay? And specifically those orbital diagrams. Okay? When S is full, okay, that's a little sphere in the center. When P is full, we have, remember, every P subshell has a PX, PY, and PZ, right? X, Y, and Z like that. Okay? So if we have 6 electrons in P, we've got 2 in X, 2 in Y, 2 in Z. Okay? and then that's completely symmetrical for all three of those, okay? Rather than one full and two half full or something like that, okay? That's the most symmetrical arrangement for those p's. So with full s and p in the valence shell, that gives us 8 valence electrons. That's generally the end point after an electron transfer. Okay? So typically electron transfers, at least for s and p block atoms, okay, will move us to that full s and p shell configuration. Okay? And that's the long-winded version of what we've been doing all semester, right, for making NaCl and for making CaCl2, right, and for making Na2O, right, giving them the right ratio so that we can add or remove the right number of electrons, okay, from each of them. Okay. So, but that's the entire general idea that happens here. And when the numbers don't necessarily equalize, right, with sodium having 1, with sulfur having 6, 1, 2, 3, 4, 5, 6, if we transfer 1 valence electron, something like that, we're in good shape with the sodium, but S looks like this, 7 valence electrons, right? And that becomes S minus, right? That ends up being 3s2, 3p5. But that's not quite going to do it for S, right? We need another electron. And when we're making ionic compounds like out of sodium and S, where would that other electron for sulfur have to come from? We'd need another sodium. Okay? This would not work with a 1-to-1 ratio because we're not making ions with full S and P subshells. Okay? We actually need more sodiums. Right? If I put another sodium in here, let's use purple or something like that. Then, oops, let's do, sorry, let's do transfer, gotta fill that hole there. Then, overall, what we end up with is 2 of these Na pluses, okay, and then 1s, which now has 2 extra valence electrons and a 2 minus charge. There, there. Now we have this grouping, this ion pair is now neutral. And it's not really a pair anymore, it's a group, right? It's now neutral overall because we have 2 of those pluses and a single 2 minus charge, okay? But it has to be neutral overall if we are truthful about how we transferred the valence electrons, okay? This ion pair up here was neutral overall, but this is not our final answer because we don't have 8 valence electrons here. So it's neutral overall, and now here we have, in this one, 8 valence electrons. Okay? So that's why sodium sulfide, its formula is Na2S, formula. Okay. Not just NaS. Okay. That sodium was fine, but that sulfur is still not filled. Okay. Throwing another sodium in allows us to get everything happy. Okay. So